All right, so before we get started on serverless computing, I want to first emphasize that the term serverless is not the best term because there are still servers involved. We're still, purchasing and using and being provisioned cloud computing resources. So of course, there's still a physical server involved. Now, the reason they call it serverless is just because you don't have to manage the servers. You don't have to configure them. So it's a lot less work. So think about serverless, less responsibility. Would that be infrastructure as a service or platform as a service, right? When thinking back to those cloud computing models, does infrastructure have more responsibility or is it the platform that has more responsibility? Which one has less? So think about where serverless would fall under, right? If, you don't have as much responsibility in managing those servers. So EC2 versus serverless computing. Again, you have a little question here. Is EC2 an example of infrastructure or platform as a service? Think back to those definitions, right? Of those cloud computing models. So hosting an application in EC2, this is usually the steps you have to do. You have to configure your instance, upload your code, and then you still have to manage the instance and your application while it's running. In serverless, you all you have to do is upload the code. So you're getting rid of step 1 and step 2, or sorry, step 1 and step 3. All you have to worry about is step 2. Scaling is automatically handled, although you can still do some adjustment of computing capacities. A lot of it is just done for you by AWS. So definitely really convenient. So key characteristics, no server management. You have the benefits of automatic scaling based on demand. And then you still have the awesome benefit, right, of cloud computing in general, which is pay-as-you-go pricing. There is one extra benefit when you compare it to EC2, is in EC2, as long as your app is running, you're paying. Even if your app's not doing any work, if it's not consuming computational resources or more extra computational resources, because when it's running, it's technically still using some. But let's say it's not using a ton of what you're paying for. You're still paying that full price in reserved instances, for example, or even in savings plan. Now, the cool thing about serverless is that if your app is idle, if it's not doing any work, you're not paying for that idle time. So it's a little bit more savings. Of course, the sacrifice is that control, right, that you get over the servers. So how is this possible? Well, a lot of these serverless applications are event-driven, so they're only going to start using computational resources based on specific triggers or events. This could be a request from a user, an upload for a file, a database operation. Can be all kinds of things. You can configure these events yourself. So they're also stateless. So they don't retain any memory of previous executions. So it's really for specific types of applications. It can't be used as generally as EC2. But for certain, uses such as like databases or storage, it could be a great option. So AWS Lambda is one of those services that is part of the serverless family. So you're only paying for the compute time that you consume, which is similar to on-demand pricing. In Lambda, you're charged based on compute resources triggered by Lambda functions. So you can configure these functions to decide, hey, start up my app whenever a user requests, right, information, or another app requests information from my application. So in EC2, you're charged for the amount of time the instance is running. There are no idle costs. That's a huge benefit. So charges apply only when your code is running. In EC2, the difference is, again, even if it's not doing work, you're still going to pay for it. And a little bit of another question here is Lambda an example of an infrastructure or platform solution? Remember, Lambda is serverless. That's a pretty big clue. Whoops, let's go to another slide if it'll let me. There we go. Not sure what's happening to my picture here. Let me try to refresh. Yeah, so I have a little graphic there of how Lambda works. I believe we're somewhere around here. There it is. So you upload your code to Lambda, you set your code triggers. The code's going to run whenever it's triggered. You only pay for the compute time that you use. So yeah, you only upload your code. You don't have to configure the server at all. You do have to set the code triggers, right? You're going to decide when does your app start. And then, yeah, if it is triggered, it will run. It's going to run on its own. You don't have to manage the server at all. And then the benefit, right, that you're going to pay for the compute time that you use. No idle costs. All right, so next is going to be a really, really big concept, which is microservices architecture. So in discussing microservices architecture, we're talking about how apps are built in the modern day. So application architecture. Well, applications, before we start talking about architecture, just know that applications are made of many different components. When you're using social media, when you're using Netflix, it's really a lot of different apps working together. Even if you're only dealing with one app at a time, that app's going to probably have multiple components. It might have a database, a server, a user interface, right? That's the front end, as they call it, business logic, so on. So there's so many components that go into an app. They all have to talk to each other, work together in order to get the app running and working. There are two ways to organize these components. There's kind of an older way of doing things and then a modern way. So the older way of doing things is the monolithic application. It's a single unified software system where all the components are bundled together into one executable unit. So UI, user interface, right? Those are your screens, your buttons, everything the user can see. Business logic, that's the backend, that's the actual data processing. Database, right? That's a key for most applications, modern day applications. You know, be able to store and retrieve data. All those components, when you kind of glue them together and they're kind of stuck together, that's called tightly coupled. That's a key of monolithic software. So what does it mean to be tightly coupled? To be glued together in a sense. It means they depend heavily on each other. So a change in one component requires changes in others. Because they're all stuck together, you can't change one component at a time. You have to change them all at once whenever you make a change in one piece. If your user interface changes, now you're going to make changes to the business logic, to the backend. If your database changes, oh, now I got to go back into the backend and make some changes there as well. In this approach to application architecture, if a single component fails, that means that everything fails. Which is not so great, right? It's best to kind of split things up and go for a microservice approach. So in order to maintain an application so that if a single component fails, the whole thing doesn't fail, you're going to want to go through the microservices approach. So microservice architecture kind of alludes that micro word, that you're splitting it up to small, tiny pieces. And each piece is independent. So it's a software development approach where applications are broken down into small independent services that while they still work together, right, they still communicate with each other, they kind of live off on their own. They can communicate through various ways, usually APIs. We're also going to talk about message brokers. I'll definitely add that to the slide. Each service is loosely coupled, meaning that it can be developed, deployed, and scaled independently. So if one fails, others don't. In my experience as a software developer, the project we were working on was a microservice architected app. So I could work on one service and seamlessly deploy it to a broader system. And our system had something around maybe like 20, 30 different microservices all working together. And it was really cool because I could work on my app. I didn't have to understand the full system, which was really complicated, right? Some people were physicists on my team. Other people were data scientists. And I was just, a junior and eventually associate full stack engineer. But I could still contribute to the team, right? I had my own entirely built by myself services that I could deploy to the rest of the team. And that would help the broader app, right, do what it needed to. So in our big ol' app, right, remember, I might have mentioned it before, maybe I haven't. So we did object detection in the sky, essentially. So, cameras have object detection. Well, we use telescopes all around the world to do object detection for like stars, satellites. even moving objects, right, such as aircraft. And of course, missiles, right? Could be a missile detection system. Anything in the sky, right? We'd be able to detect with telescopes. So my job was to create kind of a logging software to keep track of the health of the system. Another tool that we had for actually like running apps, running these microservices. I also would contribute to that microservice. So yeah, microservice is really cool because you can have a team work independently while still, putting all those pieces together and having them work. And it was cool because I could put in my system, test it out, and even if my component would break, I wouldn't have to worry about, tearing down the entire project. So tightly coupled versus loosely coupled. So look at the tightly coupled. We have an app and its service is connected to the database, to the file search, to other services. And then you have another app and it's also connected to all four of these components. And you can see the amount of arrows, right? It gets really complex. Now, if you have kind of a microservice approach, then you have one system kind of communicating to all of them without having to be so tightly connected. It's not that this database works, specifically works with this app. And if I make changes to it, then I have to make changes to everything. I can make changes to this SQL database and I don't have to mess with all these other services, and it can still communicate to all these other apps. So microservice approach makes things more flexible and a lot less complicated. So how can you even build microservice applications? Well, one of the key technologies today is containers. Containers have really made the microservice approach attainable and possible. So what is a container? It's a lightweight, standalone, and executable package that includes everything needed to run a piece of software. Back when I was testing on our software team, I would need users to test my app out. Now, if they were running it from my source code, right, if they downloaded my code, they wouldn't not only have to download the code, they would have to download like 10 other software tools that I use to run that code. So not only is building code hard, but running code is also hard because you're using all these dependencies in the modern day. I'm relying on other software in order to run my new piece of software. Containers kind of eliminate that need to download 100 different things, right, to get one piece of software to run. The container packages everything really neatly so that from like the user's perspective, you're just hitting click and run. You're downloading, running, and then all those steps of installing extra software are handled inside the container. It's really, really cool. Containers are lightweight, so they don't need a full OS. So like if you try to run a virtual machine and then like download everything there and set it up, that would take a huge amount of resources because it has its own operating system, its own kernel. Containers are kind of cool because they're still sharing the host system's kernel, so you don't have to do the work of building another operating system. So it's going to skip that step, and that's going to make them a lot faster. They're very portable, so they can run across different environments, whether you're Linux, Windows. A lot of containers, for example, in Docker are actually Linux-based, but from the perspective of the host system, right, they're not going to know what's running. It's really, really cool. So it's kind of environment agnostic. It doesn't matter. It doesn't care where it's running. It's going to run usually just fine. And again, it's going to bundle everything the app needs so that you can run anywhere you want. So if you still have questions about containers, I know, just giving you the definition is not going to entirely help. There is a video here, Docker in 100 seconds. Go ahead and watch it. Highly encourage it. I use Docker. I was a total kind of noob when I first started my job with Docker. But as I learned, its usefulness, as I kind of was expected to use it in our microservice approach, Docker became a huge tool. And I definitely became somewhat of a not expert, but definitely very knowledgeable in writing Docker files, containerizing apps, and kind of making sure things were still efficient and portable for the entire system. So yeah, definitely watch this. Docker is one of those big containerization systems. We're going to see it mentioned in some of these other slides. But yeah, Docker in 100 seconds by Fireship. Really cool YouTube channel. Anytime you have technology questions, Fireship. Uh, Shout out to that creator. All right, so containerized applications. So more key characteristics, they're isolated, so they kind of, live on their own little bubble, so they don't interfere with each other or the main system. Well, again, they can still work together. On their own, they are isolated. They're really efficient because, again, they're not using their own operating system. They're sharing the host system's OS, so it's going to save a lot of resources compared to having an entire virtual machine. So you might see that a lot when you see the efficiency of containers. They're going to compare it a lot to virtual machines, because a virtual machine you'd have to do all the work of building an entire OS, even if it's shared resources. And then scalable, you can easily start more containers to handle extra work. We're going to talk about some container orchestration software, which sounds really complicated. But basically, if you need more containers, you need more workers, you can easily scale up. So some services related to containers are going to be ECS, or Amazon Elastic Container Service. So if you want to manage a bunch of containerized apps, so you have this big project and it has 10 microservices, 10 different little components, or 10 containers. Just know one app can have, or one component can have multiple containers. It's not always one-to-one. But yeah, let's say you have all these containers working together. You can use ECS. And notice ECS supports Docker, because Docker's the most popular containerization software out there. It's a software platform that enables you to build, test, and deploy applications quickly into containers. So ECS, you can launch and stop Docker-enabled applications or container-enabled applications. So yeah, you have your app, you went with the microservice approach, you need to run it. ECS, excellent option. Now, nowadays, right, things get complicated. Like I said, when I'm building software, I'm using 10 different other software tools to build it. Well, there is a really popular software tool when it comes to running containers. So if you are using this popular software service, you're going to go with EKS. So the most popular containerization orchestration tool is called Kubernetes. So Kubernetes is a fully managed service that you can run containers on. If you want to run Kubernetes on AWS, so let's say you already set up your app to work with a super popular tool, right? Your team is using Kubernetes. You're not stuck with having to run and manage the servers on your own. You can actually run your Kubernetes app on EKS, on Elastic Kubernetes Service. So it's a fully managed service that allows you to run Kubernetes on AWS. So although you built the tool on Kubernetes, if you actually want to host it, right, make it available to users around the world, you can still use Amazon. My team did use EKS at some point. We were running our entire project on EKS, and that meant that users all across the world could use our project. And we did have users across the world, right? We were using telescopes all over the world. My team was based in Hawaii, so I flew out there a couple times to see the telescopes, and I actually got to see the project running. But we had operators in Puerto Rico. I believe we had some all over the United States. I'm not even sure where they were all at because it was a massive team. But yeah, EKS made it possible for them to access our software all over the world. So ECS and EKS are container orchestration tools. The differences are that ECS uses the AWS engine, while EKS is, you get to keep your Kubernetes engine, right? If you're a serious, development team, engineering team, you're probably going to be using Kubernetes. If you kind of want to skip that step of learning Kubernetes, because it is kind of hard to learn, ECS is easier to set up. But you're not going to have that flexibility if you use ECS, because Kubernetes is going to have allow you to manage a lot more things. It's going to have a lot more configurations. ECS is really tightly integrated with AWS services. EKS, you can have all kinds of apps running, and then you can just plop it right on EKS. ECS is kind of more, you have to use the existing services and connect them together. Speaking of containers, there's AWS Fargate. So this is another serverless compute option, just like Lambda, but for containerized applications. So again, is Fargate an example of IaaS or PaaS? Hint, Fargate is serverless, so you don't have to manage as much. That should be a big clue for which category it falls on. So you can use it with ECS and EKS. You don't have to provision or manage the servers. Fargate does all the infrastructure for you, so you can focus more on just development. You just plop your code in there. Fargate will handle all the management and configuration. So it's kind of like Lambda, but for containerized applications. So you're running microservices and APIs, go with Fargate. You're processing short-lived and event-driven functions, go with Lambda. If you have stateful applications needing persistent connections, go with Fargate. If you're doing background jobs, data processing automation scripts, so maybe stuff that doesn't have to run 24/7, go with Lambda. Batch processing with complex dependencies, so this is the containerization approach, go with Fargate. And then service API backend. So you don't have to know this slide, just giving you some differences between Fargate and Lambda. All right, so microservices and messaging. Can AWS, so this one should have a star. Let me make sure I throw one on there. Where are we at with our slides? I hate that it doesn't take me. Here it is. So yeah, this is required knowledge. I mean, we do cover it in the next slides, but it's good to throw a star there. So yeah, can AWS help with communication between microservices? We saw APIs could do that. Well, AWS does offer services that will facilitate the exchange of data between these loosely coupled microservice apps. So these apps, these microservices need to talk together. We have these messaging services that will allow you to do that. We often call these message brokers, and here are some of the solutions that AWS offers in terms of messaging. We have the simple notification service and the simple queue service, or SNS and SQS. So messaging and queuing. Here's a little video for you to watch on messaging and queuing. We'll pick up right after.